For this video, we are going to take a look at another example of a system of differential equations. We have dx dt is 2y squared minus y, dy dt is x squared y. So we got our x's and our y's all scrambled up between these two differential equations, but this is an autonomous system. There's no dependence on time for either of these equations. So we want to find the equilibrium, and then we want to find the phase plane equation. So to find the equilibrium, we are going to figure out for what conditions on x and y do we simultaneously get the x dt equal to 0 and dy dt equal to 0. And so there are several ways we could solve this system, but let's first start with the dy dt equation. So if I have dy dt equal to 0, well, dy dt, that is x squared times y. And so that's going to equal 0 only if we have either x is equal to 0 or if y is equal to 0. And so that would be the two conditions. So let's first take a look at the case. If x is equal to 0, then the other differential equation, dx dt, well, it's independent of x. So that would just look like 2y squared minus y equals 0. And so factoring that, we can factor a y out, and that would give us y times 2y minus 1 is 0. So if y is equal to 0, that we have a solution, and if y is equal to 1/2, we also would have a solution. So if x is equal to 0, one solution would be y is equal to 0, and we have a second equilibrium if x is 0 when y is equal to 1/2. So these 2 points would simultaneously make both of these equations 0. For the other condition, if we have y is equal to 0, well then the equation for dx dt would be 2 times 0 squared minus 0. So the equation for dx dt is going to be equal to 0 no matter what value of x we pick here. So in other words, if y is equal to 0, that's going to guarantee that both differential equations are 0. So any point of the form x comma 0, so every point on the x-axis is going to be in equilibrium. And so notice we have infinitely many equilibrium in this for this differential equation. So we don't have to only get one equilibrium. Okay, so next let's take a look at the phase plane equation for this system, and then we'll solve that phase plane equation. Okay, so the phase plane equation, dy dx, we get that by taking the ratio of these two equations. So to find dy dx, we would take dy dt on top, x squared times y, and then we would divide that by dx dt on the bottom. We would get 2y squared minus y. And so before we solve this, we can simplify by factoring a y from the numerator and the denominator, canceling them out. So we get x squared over 2y minus 1. And yes, once again, this is a separable differential equation. So we can separate our x and y terms. So I can bring the 2y minus 1 over to the left side, and I bring my dx over to the right side, and we've got pretty simple integrals on each side. So integrating the left side, we would get y squared minus y, and on the right side, we've got x cubed over 3 plus c. And so if I want to put everything on the same side of the equation, I would have y squared minus y minus x cubed over 3 is all equal to c. So that would be the solution to our phase plane equation. And again, this is an implicit solution. We can't give an explicit solution for y because solving for y, we would not get unique solution for y. So it's fine to leave this solution in implicit form.